software engineer, and I contributed in this project by by assigning team duties and developing and designing the website database and multiple components in the system.
Hi, my name is Michael Ramlakan. I was the hardware lead engineer. I assisted Arturo in assigning roles and contributed by handling all electronic components such as the wiring, case design, soldering for station, and integration between software and hardware.
I'm Beer Giordano. I'm the software lead engineer. I developed and designed the website alongside Arturo and program components such as the thermal sensor.
And my name is Leonardo Kamash. I'm the hardware engineer. I help test and solder equipment. I created schematics for the system and built the case. So what inspired us to pursue our project? Just in New York State alone, 2.04 million COVID-19 cases caused around 50,000 deaths. The main reason why we wanted to complete this project was to develop a cheaper and more effective thermal scanner, to develop a universal database for all users, and to help prevent the spread of COVID-19. Some market information that I just want to mention here is disposable face mask market is valued at 74.5 billion in the first quarter of 2020, is expected to go up 50% over the next 7 years. And the body temperature sensor market is projected to reach around 8.8 billion by 2027.
So the big picture here is that our social distancing standards aren't always being met, and even when they are, it's very important to give users and institution organizers access to their body temperatures so they can make a proper medical decision. And it's also important to supply sanitary items to help prevent the spread of the disease.
Some related works that our projects are based off of is the King County's Metro Ready When You Are station, the city's farmers market station, the kiosk thermal station. What this chart is a pros and cons chart compared to our thermal imaging COVID station. And a key takeaway from our station compared to these is that ours would be able to accurately obtain temperature and upload it to our database for our users to use. This chart shows our selection method of methods we defined as necessary for our station to have, which is our design size, our system tracker, and restock value compared to our competitors. And as the score shows, our thermal imaging COVID station's proposed idea should outscore our competitors.
And here we have the project description of our project. Essentially, users will go into our website, create an account, and they will be presented a QR code that is unique to them. Then they will come forth to the system and present this QR code at the system and have it scanned. Once they scan it in, they'll be prompted into the scanning process. And once they're finished with their scan, their results will be emailed to them. The system is also outfitted with a face mask dispenser, so that if anyone who doesn't have a face mask can obtain one here. The whole system is contactless, meaning we use multiple motion sensors for both the system and the face mask dispenser so we can stop spreading the disease. And the components that the system uses includes the Raspberry Pi, motion sensors, cameras, thermal sensors, stepper motors, just to name a few. And we hope that the system will help keep people safe.
As far as the impact of a project goes, there's a high demand for safety and sanitation projects in heavily populated areas, especially for institutions such as schools and offices. So for this project, we wanted to help keep institutions and the people in them safe by minimizing the risk of potential carriers and helping them realize they shouldn't enter the institution if their temperature is too high.
As Arturo was explaining in the project description, the system should be able to utilize the temperature taking technology. It should be able to update the user information. Also, results should be emailed to the user. As you can see here on the right, this is the way the user is supposed to interact with our system. Some other key components for our system would be it should be cheap to produce and allow for more distribution. Website should be simple to sign into, and each user must have a unique QR code. Here we have our system architecture diagram, which is basically a breakdown of the Raspberry Pi microcontroller and how it's utilized in our system. Here we have 6 main tasks broken down into 3 subcomponents. So in the subcomponents, it's just explaining how the Raspberry Pi is utilized positively against the 6 main tasks.
And here we have the related theory. Some key takeaways about this is Planck's law, emission from object, reflected emission from ambient sources, and emission from the atmosphere. And we at the bottom here, we have this total radiation power. And the reason why this is important is because we are utilizing a thermal scanner. And the way thermal scanners work is they have to measure the background radiation along with their object radiation, which would be the user. And this is then used to calculate accurate temperature reads.
Some key takeaways for our hardware design is the use of a Raspberry Pi microcontroller for the microcontroller for our main system. Some key things that the hardware team had to do is program the electronic components involved in the system, such as the LCD screen, stepper motors, Raspberry sensors, and so on. We included the LCD screen because we wanted the users to have an emergency contact just in case they are not able to sign in using their QR code sensor, their QR code image. We used the infrared camera because we wanted the station to be functional during high light and high and dark light, meaning the station would be operational during night and day. Because of this, we had to implement a 5-volt transformer, a 5-volt 2-amp transformer that powers our Raspberry Pi, and then from our Raspberry Pi, as the image, the PSpice image shows in the right, then powers our thermal camera and then to our boost converter. What we've done is implemented a boost converter that allows us to boost the 5 volts coming from the Raspberry Pi into another circuit that then powers our other electronics, such as the motion sensors, the stepper motors, the fans, the sensors, and so on. And with the help of the coding team, we were able to implement all of these together.
Here we have our hardware iterations to develop optimal design. So the hardware team created an optimal design of a circuit using a transformer, resistors, and boost converters that could be used to power all the electronic devices. We refined the hat stepper motor code to ensure the dispensing mechanism operates properly. We integrated all the sensors to the system and created a case to display and store all the items.
For the software design, we developed, like Arturo mentioned, we developed a website where you can see in the image on the upper right. We've implemented a working user account system for users to receive their QR codes, and using the station, we'll also send that user an email with their temperature reading. Underneath that picture, you'll see that we developed a database for the website to contain all user account information, including their QR code information, and a second database was made for the station itself to keep track of who uses it and when. On top of this, we've also programmed all the system components to always be operating at the station.
Here we have the software iterations to develop an optimal design. Our software team was able to do this because we were able to update the website to make it look more appealing and readable on mobile devices. We had to fine-tune the thermal scanner because based on the previous readings, it was not that accurate, and that was due to the scanner having a low resolution. We had to discard the original physical QR scanner since it was not programmable. Instead, we opted to use a QR scanner in the camera itself, which we programmed. And then we created a prompt which will utilize all the systems in the system. Mike?
I'm sorry, my mic was muted. I apologize. So this chart shows the integration test for our project. The first step shows the operation where we had to analyze all the specs of our components to determine the voltage that was necessary in powering the entire system without hindering any objectives. So initially we first failed this step because we realized that there was an initial need of 24 volts, which our Raspberry Pi was not conducting, which is why we used a boost converter. And in our next slide, we were able to fully boost our circuit and power all electronics, the Raspberry Pi, the motion sensor, the fan, and everything to work properly and together. After integrating all of that, we were then able to take it a step further and integrate and combined our efforts with the coding team and finalizing the website on the system.
Here we have our components acceptance test, and as you can see here on the left, we have two graphs. The first graph shows a hat stepper motor and a speed versus voltage test, and as you can see, that as the voltage increases, the speed of the motor increases, and this is important because our face mask our face mask system utilizes these stepper motors to output a face mask. So we have to make sure that the right voltage is inputted so that the motors can turn properly and dispense the face mask accordingly. The second one is the PIR motion sensor with an activation time versus voltage. And as you notice, as the voltage increases, the activation time decreases. And since the whole system is contactless, we need to make sure that these motors are working at good operational temperatures, and the speed of them is the detection speed of motion should be reduced.
Here we have our corrective actions and iterations charts. So here we have 6 tests that we've completed over the course of the year with failed success action and corrective action and amount of iterations that we've done. Just to take an example of one of them, we did a face mask dispensing one last week. As you see there at the bottom, we named the test ID dispenser 1, the test type software test. So for the failed or success action, we successfully solved this software pin issue, which we were having. The corrective action is we were able to convert the code from board to BCM, and this solved the error that was appearing on our screen. And you see, we only did it for one iteration.
This is our project completion and future work. In our project, we learned several new skills in both software and in hardware. We were able to create a large-scale project based on current events, and our team was able to create QR codes for every user. Like Mike said earlier, the QR codes could be detected both in day and night. We have databases for both for the website and for the station itself. We created a case, we reduced the system temperatures, increased the overall output with the boost converter, and we were actually able to complete the project. In the future, we potentially could add more stuff such as sanitation equipment like wipes and sanitizer. And seeing how the QR system already logs date and time, perhaps we could use, businesses might want to have a time clock system in use, which will allow them to see when their employees clock in and out of their business. We could also plan to make it more lightweight, and the reason we could do this is by maybe 3D printing the case instead of making it out of wood.
This is our project schedule. We started off by creating blueprints, ordering parts, learning to design a website. Before in the winter, we moved on to testing parts and developing website. In the spring, we built the system itself and programmed its components, and as of late April, we've done the final testing on everything.
So these are the challenges and previous refinements. Like some of the challenges that we faced during the semester with our system is overheating issues, power issues, and then issues with the face mask dispenser itself. So the way we combated these issues and solved them is by purchasing a fan to reduce system temperatures. The power issue was solved by purchasing a boost converter, which put more voltage in the system. And then the face mask dispenser, as Leo said earlier, we had an issue with the pins with the Raspberry Pi, that there was an issue. So we were able to solve the issue by converting the pins into BCM mode rather than board mode. And some of the refinements that we've done in the past couple of months in terms of hardware is that we finished testing all the components. We reduced system temperatures. We added motion sensor capabilities to the whole system. We created a working face mask dispenser and developed the case. In terms of software, we were able to design and create a website. We generated personalized QR codes for every person. We overhauled the website look. We created an easy-to-use prompt, and all the results will be emailed to the user.
So what this chart shows is a bill of materials that our project has used. So some key notes to take away from our project is that Dr. Wang has provided us with the Raspberry Pi Model 3B and 7-inch touchscreen display, which is a huge part of our project, and we appreciate him for that. And because of that and all other components involved, we were able to reduce the cost to $243.
So here we have a demo video demonstrating our system in action. And that concludes our video. And here we have the code standards and constraints. We utilized health and safety codes from New York City, and our system implements Article 11 because it encourages users to go home if they are sick. It encourages Article 11 because it helps prevent disease and help spreading it unknowingly. And since our system is hands-free design using the motion sensor, it is hands-free. And Article 45 is implemented in our system because it keeps tracks of all the users and who uses it and what time they use it. And some of the standards that we utilize in the system is IEEE 802.11, which allows for Wi-Fi adapters in the system, and the ISO IEC WDTR 24772-4, which allows our system to utilize Python code.
Here we have the ethical analysis. So in the future, we would like to have this stationed at schools or at a workplace, places where there are a lot of people or densely populated areas. Some potential ethical issues that we can come across are privacy. Even though we do have some security built into our system, maybe over time it could be improved a little bit more. So the IEEE and SPE codes that apply to our project. So our project is never going to be, it was never based on harming anyone. So that's why we made it hands-free, make it as safe as possible to use. Also, everything that we did, as you've seen through the Gantt chart, we did a lot of research and conducted a lot of mock simulations before we implemented anything into our project. Some recommendations to avoid ethical concerns could be display messages and visual images that comfort the user.
And as for the engineering complexity of the project, for one, we've managed to have current safely dissipate through the components without harming their performance. And we've also integrated them together for the system base. We've developed a QR code system linked between the system and users to keep the system contactless while also accounting for security and privacy. Building and optimizing the system required skill in both electrical and computer engineering, as well as mechanics for practical use. And we learned multiple tools that we'd use for the project's development and design.
And here are some of the references we used in our project. I'd like to thank everyone here, and are there any questions?
Any questions?
Thank you.